Hello everyone, my name is Tony. I'll talk about how to build device-independent protocols from computational assumptions. And really this is referring to two protocols. So one is for self-testing, and this is joint work with Thomas Vidick. And one is for device-independent quantum key distribution, and this is joint work with Rotem, Arnon-Friedman, Andrea, Coladangelo, and Yfke, Dulek. So let me give you some sense of how this is going to go. So I'm going to start by reminding you of the setting for standard DIQKD, and given that this is QCrypt, I'll keep this fairly brief. But the basic sort of point here is that security of the final key is based on a Bell inequality violation. And then we will introduce a new setting, which we'll call the computational DIQKD setting. And in this setting, we've removed one assumption from the standard setting, which means we can't base security on a Bell inequality violation. So we will need something that replaces this Bell inequality violation, and this will use a new assumption that we introduce here, which is a computational assumption. And the main technical tool underlying this is what we call computational self-testing, and you can really think of this as being what replaces a Bell inequality violation. Okay, so we'll get into much more detail about these 2 points here later on. So let me start with a standard setting. Even just in normal device-dependent QKD, we always have three parties, Alice, Bob, and Eve. And Alice and Bob are connected by a public classical channel. And what they would like to do is they would like to turn this into a private classical channel, so Eve can't read everything that they are telling each other. And the additional resource that they have for this is shared entanglement. So really the task in QKD is turning a public classical communication channel and shared entanglement into a private classical communication channel. Now we need to be a bit more precise here by what we mean when we say shared entanglement, because Alice and Bob are just classical people. So really what this means is they have some quantum experimental setup, some quantum device, which they can interact with classically just by pushing buttons and reading stuff off a display. And these two devices here, they are what share entanglement. And what makes such a protocol device independent is if we don't want to place any assumptions on what these quantum devices do inside. So for example, this device might have a button which says make computational basis measurement, but Alice doesn't want to assume that when she presses this button, the device actually does do a computational basis measurement. Okay, so the device can just do whatever. We don't want to make any assumptions about the device. And also because we don't want to make assumptions about the device, we include for the possibility of the device sharing entanglement with Eve. So then how can we still hope to get a secure key for Alice and Bob in this setting? Well, the basic gist is that Alice and Bob, in their classical interaction, will run a sort of Bell test and then use this classical communication here to check the winning probability or the winning conditions in that Bell test. And if they observe a Bell inequality violation, then this will allow them to make some sort of statement about the device's states and measurements. And from this, they can get an information theoretically secure final key. And this information theoretic security here just means that there are no computational assumptions involved, and Eve, even if she's arbitrarily powerful computationally, won't be able to do any better at finding out any information about the key than just by random guessing. Now, I want to stress here that even though this device is untrusted and it can share entanglement with the other device or with Eve, it can't communicate to the outside world. So we could draw these boxes to kind of highlight this fact, but okay, we won't because the figure gets busy. But we'll have the convention that whenever there is no explicit communication channel indicated, communication is forbidden. So this picture sort of, these three connections here, they all mean entanglement but no communication, and kind of looks as though they're all the same. And technically they are, but in the role that they play in DIQKD, they're really quite different in the following sense. So why is it forbidden that the device can communicate with Eve? Well, if it could, then it could just forward its entire interaction with Alice to Eve as well, and likewise for the second device. And then Eve would know everything that Alice and Bob know, and clearly Alice and Bob can't generate a secure key from that. Okay, so the communication from the device to Eve sort of must be forbidden almost trivially. Whereas the communication between the two devices here, the reason that this is forbidden is really because we rely on a Bell inequality violation, and for this to be meaningful, we need these two devices to be isolated from each other. But it's sort of not on the same level of impossibility that this non-communication assumption couldn't be removed. And secondly, this entanglement between these two devices here, this is something that an honest device will have and will use up in the protocol. So a device that behaves as intended would measure entangled states in the protocol and hence use up this entanglement. Whereas this entanglement to Eve here is something that an honest device wouldn't have. So what that means is that between runs of the protocol, we need some way of replenishing this entanglement. So we need some way of distributing quantum states across these two devices to sort of stock up an entanglement for the next run of the protocol. And from an implementation point of view, this puts us in a somewhat awkward position in that between runs of the protocol, we need quantum communication between these two sides. But during runs of the protocol, we need this assumption that the two devices can't communicate with each other. So this is not impossible to achieve experimentally, but it may be more or less challenging depending on what sort of setup you choose. Now, what we want to do here is, just say, well, let's just take a permanent quantum channel that's always open between these two sides and see what we can still say. So if we modify the setting in this way, then it ends up looking something like this, where now you can either think of this as two devices connected by a quantum channel, or you can also think of it as just one big device that has one sort of terminal for Alice and one terminal for Bob. And as before, this device is untrusted, but we can't rely on our previous DIQKD proof strategy because now that these two sides can communicate, a Bell inequality violation is meaningless. So to replace this Bell inequality violation here and get a proof of the ground, if you like, we need to place a new assumption on this device. And this assumption is a computational assumption, and what it says is that this device is assumed to be unable to break a certain post-quantum cryptographic primitive called learning with errors. And what this will allow us to do is replace this Bell inequality violation by some interactive protocol that leverages this computational assumption. Now, what I really want to highlight here is that this is a computational assumption on the device. It's not a computational assumption on Eve. So Eve remains computationally unbounded as in standard DIQKD. And secondly, this computational assumption is only required for the duration of the protocol. So once you are sure that for the duration that you ran the protocol for to generate the key, this device didn't break this post-quantum crypto primitive, then the final key that you get out is still information theoretically secure. It still has the same level of security as from standard DIQKD. Okay, so this is this computational DIQKD setting and the basic proof strategy that one would follow here. Now, for the remainder of the talk, I mostly want to talk about this interactive protocol, which is this computational self-testing, which I mentioned at the beginning. But before I do that, I want to highlight one additional requirement that we want to satisfy in this setting. And that's the following. If we compare the standard setting to this computational one, then one feature for the honest strategy in the standard setting is that clearly because you only have local devices, it can succeed by just performing local operations and using pre-shared EPR pairs. And this is a property that we want to preserve for the computational setting. So we still want to keep this requirement that an honest device should be able to succeed just with pre-shared EPR pairs and local operations, even though a dishonest device may make use of this quantum channel here in whatever ways it wants. Okay? And the reason that we insist on this requirement is that we would imagine that this kind of computational protocol would be executed in a setting where you are somewhat sure that these two devices can't actually communicate. So you hope to be in this setting, But because you have this quantum channel lying around connecting the two sides of entanglement distribution, you're maybe not like entirely sure and want to place an additional sort of level of security on top of this if this communication between the two sides is a major security concern. Okay, but obviously if you hope to be in this setting, then you would want that an honest device can also succeed in this setting. All right, so now for the remainder of the talk, I'll talk about this computational self-testing, which is sort of the replacement for the Bell inequality violation. And let's first state what exactly we want from this protocol. So it's going to be some classical interactive protocol run by Alice and Bob on this device, and the device can either win or lose at the end. This is just some terminology. So Alice and Bob have some conditions that they check, and we say that the device wins or loses whether or not it satisfies these conditions. So the statement that we would hope for is that if a computationally bounded device wins with probability at least close to 1 in this protocol, then the state prepared by the device must have been an EPR pair, and the device must have measured each qubit of this EPR pair in the bases requested by Alice and Bob. So you can imagine that this device on Alice's terminal here has 2 buttons, computational and Hadamard basis measurement, and we want that these buttons actually correspond to the true measurement that the device is performing inside. Now, all of this is only going to hold up to global changes of basis, just because Alice and Bob only ever see classical measurement outcomes. So if the device changes basis, so applies some unitary or some isometry to both the state and the measurements, there's no way that Alice and Bob can check this. So just as a brief aside, for those who know self-testing well, usually in standard self-testing we only allow for local changes of basis. This we can't do because these two sides are connected, but it turns out that these global changes of basis here, they are still, fine. You can still do DIQKD based on self-testing, even if you allow for these global changes of basis. Okay, so before I move on to actually explaining how this protocol works sort of on the inside, let me mention some previous work. And this previous work is usually in a setting where you have just one device with one terminal and one classical user, but it's not too much of a jump from the 2-port setting that I've shown so far. So the setting and a lot of the tools that we also use in it were introduced in 2 works. The first on certifiable information theoretic randomness expansion by Berkeley and others from 2018, and the second one, this well-known Mahadev verification protocol. And a third piece of work that I want to mention here is a protocol for what is called remote state preparation from Georgi and Vidick from 2019. And this achieves a task which is very similar to self-testing, but for a single qubit rather than an EPR state. So I want to explain in a bit of detail how this protocol actually works, because we can use this as a building block for explaining how our self-testing protocol works. So let's see how this goes. So we start by fixing some set of single qubit states, and for concreteness you can just think of the computation and the Hadamard basis states here. They can do 10 states in total, but we'll just need these 4 here. And then in the protocol there are some setup rounds that make some clever use of post-quantum crypto, and at this point in the protocol here, an honest device, so one that behaves as intended, would have prepared one of these 4 single qubit states. It then receives a measurement basis from the classical user, the verifier, so either computational or Hadamard basis, and an honest device would measure its prepared qubit in this basis and report back the result. And now the guarantee is that if the device succeeds in all of the checks that the verifier applies here, then indeed it must have prepared one of these 4 states psi I and measured it in the requested basis. Okay, so I hope you can see why I said this is a bit like self-testing, but for a single qubit. It also makes a statement about the state and the measurements that this device performed. Now, one additional requirement that we will use in the self-testing protocol for EPR pairs is what is called blindness. So this means that the verifier, the classical user here, knows which one of these 4 states the device has prepared, but the device itself actually doesn't know. So it prepares these states, blindly, in the sense that it doesn't know what it actually has prepared. And the reason that this is possible is because we use post-quantum crypto here, and the device cannot break this crypto. Okay, so if we want to build on this remote state preparation protocol to get a protocol to self-test EPR states, what do we need to do? Well, firstly, the EPR state is a 2-qubit state. So we somehow need to show that the device has 2 qubits. And what this means is that Alice and Bob need to enforce a tensor product structure on this device's global space. And they need to do so only using this classical communication and leveraging the post-quantum crypto. Secondly, we don't just want the device to prepare a 2-qubit product state, but we actually want it to prepare an entangled state, an EPR state. So we somehow need the device to create entanglement with respect to the tensor product structure that Alice and Bob enforced here. And thirdly, as I mentioned before, an honest device should only have to use local operations and pre-shared EPR pairs. Okay, so I won't say too much about this first step simply because it's very technical and very hard to give intuition for, so we'll focus on how these last 2 steps can be achieved. And to start, let's consider a setting where Alice and Bob each have 1 device and these 2 are isolated. And now if Alice and Bob each run a remote state preparation protocol on their device, then just by virtue of this protocol, we know that each device will have prepared one of these 4 single qubit states. So now comes the first step from this slide, which, as promised, I won't explain too much. And it says that if Alice and Bob still run 1 copy of the RSP protocol, but now on 2 terminals on 1 such big connected device, then essentially any device that succeeds in these 2 protocols must treat the 2 RSP protocols independently, in the sense that it still must prepare 2 qubits, the sort of 1 corresponding to Alice's RSP protocol and 1 corresponding to Bob's. Okay. So this way we can have the device prepare 2 qubits, and now what we need is that these qubits somehow become entangled. So for this, let me rewrite these as follows. So this just means the 4 states 0, 0, 0, 1, 1, 0, 1, 1, and so on. And now a sort of obvious idea to turn these into entangled states is to ask the device to apply a CNOT gate on these 2 qubits. Now there are 2 problems with this. Firstly, the CNOT gate is a non-local gate between these 2 sides. And as I said, we want to avoid this. We want an honest device to be able to succeed just using local operations and pre-shared EPR pairs. And secondly, we somehow need to certify that the CNOT gate actually has been applied, right? We can't just take it on faith that the device does this. So for the time being, let's ignore this problem that it's a non-local gate and just focus on how we can certify it. And to see how this can be done, let's see what would happen if the device were to apply this CNOT gate. And you can just do the calculation and see that these first 3 families of states here, they won't change. So the state will change, but it will remain within the same family. So 1, 0, for example, gets mapped to 1, 1, which is still the same kind of product state. And in contrast, these last 4 states down here, they will get mapped to the 4 Bell states. So why is this useful? It's useful because it basically tells us that in these first 3 cases here, the CNOT gate doesn't do anything except some relabeling. So if Alice and Bob in their checks undo the relabeling and then apply the same checks as they did for just the 2 independent RSP protocols, then they can use these first 3 cases here to certify single qubit measurements in the device. And in this last case then here, Alice and Bob can check whether the device returns bell-like correlations. And by this I just mean whether the XOR of these 2 bits is what it should be. And for this, Alice and Bob will use their public classical communication. Okay. So with this, we've gotten single qubit measurement certifications, but we somehow need to apply this certification to this last Bell case down here as well. And the reason why we can do that is this blindness property that I mentioned earlier. So remember that this said that the device doesn't know which one of the 4 states from the RSP protocol it has prepared, and therefore in particular doesn't know which one of these 4 cases it is actually in. And at least intuitively, this means it can't sort of change its behavior based on which case it is in, and therefore we can combine these 2 statements and certify single qubit measurements on a Bell state. Okay, so this achieves what we wanted from a self-testing protocol. The only problem that remains is that this is a non-local gate, which we don't want. So to get rid of this non-local gate, we can use a trick, namely gate teleportation. And what gate teleportation does is it basically sort of implements a CNOT gate using only local operations and pre-shared EPR pairs. So if Alice and Bob have each prepared some local states, phi and psi, and want to apply a CNOT gate, what they can do instead in gate teleportation is have some pre-shared EPR pair, and then do local measurements, so measurement just on Alice's system and the A part of the EPR state, and likewise for Bob and the B part. And they will do these measurements, get back some bits A and B, and if you choose these cleverly, and then this can be done, then the post-measurement state will be the CNOT gate applied to these original states with some sort of correction operator on top. So this correction operator now is the only difference to the actual CNOT gate. And to deal with this, we can just have the device send this bit A to Alice and the bit B to Bob. And then Alice and Bob can kind of undo the effect that this correction operator had on the device's answers in the RSP protocol and check the conditions from the RSP protocol on these corrected answers. Okay, of course you need to check that this doesn't introduce any new ways for the device to cheat, but it turns out that it does not. All right, so now we've really achieved what we wanted. We have a way of certifying Bell states and single qubit measurements on these Bell states, and an honest device using gate teleportation doesn't have to do any non-local operations as long as it has pre-shared EPR states. Okay, so let me wrap up. The main result that we showed is that you can build self-testing and DIQKD protocols that don't rely on Bell inequalities, and therefore also don't need this non-communication assumption between the 2 devices. Of course, as I sort of stressed in the beginning, we still need non-communication to Eve because otherwise it's clearly impossible to generate a secure key. And the alternative assumption instead of this non-communication assumption is that the device cannot break post-quantum cryptography during the protocol. But in particular, this still means that the final key remains information theoretically secure. So this is really an assumption that only applies to the device and only applies temporarily. And the main technique underlying this is this tried cryptographic leash, if you like, for black box quantum devices, which was introduced by Berkeley and others and Mahadev. So in terms of future work, I think there are a couple interesting directions. Firstly, we can only self-test EPR states right now. Obviously, we would like to extend this to a larger class of states. Secondly, the QKD security proof right now is in the IID setting. So one would really have to extend this to the non-IID setting as well. And the reason this is non-trivial is because entropy accumulation doesn't quite work here. So some new ideas are needed. If you actually want to make the QKD protocol itself more efficient, one could try to do this without explicitly going via self-testing, because in the standard Bell-based setting, it's known that going explicitly via self-testing is kind of not the most efficient route to get DIQKD. So perhaps something more direct is possible in this computational setting as well. And finally, just more broadly, I think there are sort of lots of possibilities to build other interesting applications based on these cryptographic leash techniques from these papers here. Right, so I'll end here, and thank you very much for watching.